In this video, we're going to be looking at acceleration in gravity, and this is video 4 out of 6 for our forces topic. Let's get right into it. Acceleration is the change in velocity divided by time. Acceleration is where something gains speed, i.e. gets faster, or when something changes direction. Deceleration is where something loses speed and gets slower. If you know the change in velocity, so the starting and final velocity, and the time taken, you can work out the acceleration or deceleration. Acceleration is equal to the change in velocity divided by time, where acceleration is measured in meters per second, or meters per second squared. Change in velocity is measured in meters per second, and time is measured in seconds. Let's do a worked example now. A truck performs an emergency stop after Nana Margaret steps out onto the road. It comes to a complete stop from 20 meters per second over a time of 3 seconds. Calculate the deceleration of the truck. Okay, so our acceleration is equal to the change in velocity divided by time. Our change in velocity is 20 meters per second, and that's because it goes from 20 meters per second to 0 meters per second because it comes to a total stop. That means our acceleration is 6.66. The unit for acceleration is meters per second, or meters per second squared, so my final answer is 6.66 meters per second. Another worked example now. A train accelerates from 40 meters per second to 65 meters per second in 30 seconds. Calculate the acceleration of the train. Okay, so our acceleration is equal to the change in velocity divided by time, where our change in velocity is 65 take away 40, because that's the difference. The time taken is 30 seconds. 25 divided by 30 is 0.83. Since acceleration is measured in meters per second, or meters per second squared, our final answer is 0.83 meters per second squared. On top of distance time graphs, there is also velocity time graphs. So in our last video we looked at distance time graphs, and just to confuse you even more, we're now going to have a look at another type of graph, a velocity time graph. So velocity time graph show variation in velocity with time. So on the y-axis we'll have velocity, not distance. This means the way we read it is different to a distance time graph. Let's have a look at this video which explains it a bit further. Hello there. We're going to be looking at velocity time graphs. We have already looked at distance time graphs. Distance time graphs show how distance varies with time. If an object is moving in a straight line, we can look at velocity time graphs, which show an object's velocity and how it varies with time. Straight lines on velocity time graphs show us that an object is travelling at a steady speed. This is intuitive. A horizontal line means there is no change in velocity with time, so it must continue at the same velocity. Straight lines along the time axis mean there is no velocity. The object is staying still. We say it is stationary. A slanted line shows us that the object is accelerating. Again, this makes sense as with time the object is gaining velocity. It is accelerating. A line with a negative gradient tells us that the object is decelerating. With time, the object is losing velocity, so it is slowing down. A curved line on a velocity time graph means we have acceleration or deceleration with an increasing or decreasing rate. If the gradient is getting steeper, the rate is increasing, and if the gradient is getting less steep, the rate is decreasing. The acceleration of an object is given by the gradient of the line in a velocity time graph. We can determine an object's acceleration by determining its gradient. Here is the equation for the gradient of a line. The gradient is equal to the change in y divided by the change in x. If the line is curved, we can draw in a tangent and measure the gradient of that instead. Here is a velocity time graph for a car on a motorway. Determine the deceleration of the car between 6.5 seconds and 10.5 seconds. Get values for the change in x and change in y. The change in y is 15 take away 5, which is 10, and the change in x is 10.5 take away 6.5, which is 4. The gradient is equal to the change in y divided by the change in x, so the gradient is 10 divided by 4. 10 divided by 4 is 2.5. Since our gradient is equal to the deceleration, our deceleration is 2.5, and since acceleration and deceleration is measured in meters per second, our final answer is 2.5 meters per second. Work out the acceleration of the car at 10 seconds. So firstly, we are going to get values for the change in x and the change in y. To do this, we are going to have to draw a tangent at 10 seconds. The change in y is 15 take away 5, which is 10. The change in x is 20 take away 5, which is 15. The gradient is equal to the change in y over the change in x, which means the gradient is 10 divided by 15. 10 divided by 15 is 0.667, and since gradient is equal to the acceleration, our final answer is 0.667 meters per second. Explain what is happening in this velocity time graph. At the start, we have a straight line with a gradient of 3.125, so we have an acceleration of 3.125 meters per second. Then, at 4 seconds, the object moves at a constant velocity of 12.5 meters per second, before decelerating at a rate which increases with time after 8 seconds. There is one more interesting property about velocity time graphs. You can determine the distance travelled by an object by looking at the area underneath the graph. Using geometric shapes like squares, rectangles, triangles and quadrilaterals, you can determine the area. Determine the total distance travelled by this car in the first 20 seconds of its journey. Firstly, we are going to split the area up into manageable chunks. Find the area of the shapes underneath the graph. Firstly, we have a rectangle with width 6.5 and height 15. 6.5 times 15 is 97.5 meters. Next, a quadrilateral with side length 15, side length 5 and width 4. Using our equation for the area of a quadrilateral, we can find that the area of this is 40 meters. Next, we'll have a rectangle with side height 5 and width 9.5. 9.5 multiplied by 5 is 47.5 meters. Now add them all up. The total distance travelled is 97.5 plus 40 plus 47.5, meaning the total distance travelled is 185 meters. So that shows all of the basics of velocity time graphs, and it shows you how to calculate the distance travelled when you have a velocity time graph as well. So to find the distance travelled, you just look at the area underneath and you can find the area with all of the different equations, like the equation to find the area of a rectangle, the equation to find the area of a quadrilateral, or sometimes even the equation to find the area of a triangle. So velocity time graphs show velocity versus time. This velocity time graph shows a train accelerating and then travelling at a constant speed. So this line here, which is a slanted line, this shows that as time goes on, the train gets faster. So that means a slanted line on a velocity time graph shows an acceleration. As time goes on, the train's velocity here does not change. It's travelling at a constant speed. So on a velocity time graph, a line which is going horizontal shows a constant speed. So what's the difference between the graphs? Straight lines on a distance time graph mean an object is stationary. Straight lines on a velocity time graph mean an object is moving at a constant speed. Straight slanted lines going upwards mean travelling at a constant speed on a distance time graph, but mean acceleration on a velocity time graph. Straight lines going down on a distance time graph mean an object is travelling back towards you, whereas on a velocity time graph it means slowing down or deceleration. Curved lines on a distance time graph mean an acceleration, and on a velocity time graph it means a change in acceleration. The acceleration of an object can be found by finding the gradient of a velocity time graph. This can be done by using the gradient formula, just like for finding the velocity on a distance time graph. So remember, the gradient on a distance time graph is speed. The gradient on a velocity time graph is acceleration. And one final thing about velocity time graphs, which was covered in that little video, the area underneath the graph can be used to find the distance travelled by an object. So, going back to the velocity time graph for the train, we can use the area to find out the distance it has travelled. So, looking at this velocity time graph, we can see that underneath we'll have a triangle and we'll have a rectangle. So the first thing we do is split it up into two manageable chunks. The area of the triangle, because it's a right angle triangle, is half the base times the height, and the area of the rectangle is simply the base times the height. So half of 20 multiplied by 20, which is for the triangle, is 200 metres. 40 multiplied by 20 is 800 metres. So if you add both of those areas together, you get 1,000. So that means the total distance covered by this train is 1,000 metres. If you're following along in your revision workbook, pause the video now and complete task 14. And note there is more than one page for this task. Okay, so we're going to move on now. There is another equation relating to acceleration. For uniform acceleration, you can use another formula. I know, formulas are getting too much. Luckily, this one is given to you in the exam, so you don't need to remember it. You only need to know how to apply it. And that equation is final velocity squared minus initial velocity squared is equal to 2 times the acceleration times the distance travelled. So the next equation which you need to know is v squared minus u squared is equal to 2as. Don't worry, this one is given to you in the exam, but you need to know how to use and to rearrange it. So let's have a look at a worked example. A car begins at the speed of 3 meters per second and accelerates at 2 meters per second squared over a distance of 40 meters. Calculate the final speed of the car. Okay, so we're going to write out our equation. V squared minus u squared is equal to 2as. So it wants the final speed of the car. So our unknown here is v. V squared minus 3 squared, and the reason this is 3 squared is because it begins at the speed of 3 meters per second and the u is the starting speed. So we're going to ring 3 into the equation. We've got 2 multiplied by the acceleration, which is 2 meters per second squared, multiplied by the distance travelled, which is 40 meters. So v squared minus 3 squared is equal to 2 times 2 times 40. So simplifying the right hand side, 2 times 2 times 40 is 160. Well, 3 squared is 9. So v squared minus 9 is equal to 160. So we need to add 9 to both sides to get v squared by itself. So if we add 9 to the right hand side, we get that v squared is equal to 169. V squared being equal to 169 means that v is equal to the square root of 169. The square root of 169 is 13. So our final velocity is 13. Final velocity is just a velocity, so it's measured in meters per second. So our final answer is 13 meters per second. If you're following along in your revision workbook, pause the video now and complete task number 15. Near the Earth's surface, any object has an acceleration downwards at 9.8 meters per second squared. This means all objects accelerate the same amount. So if you drop a bowling ball and a piece of paper, both will accelerate at the same pace. This is because gravity affects large bodies, like the Earth. The Earth is so massive that it has its own gravity. So, we're going to have a look at fluids. Do you know what a fluid is? A fluid is a substance which is a liquid or a gas. So of the three states of matter, it qualifies as a fluid if it is either liquid or gas. Originally, all objects accelerate the same amount, but after a while, you get forces trying to oppose the acceleration. These are known as resistive forces, and they work in opposite direction to acceleration. Look at what happens to this skydiver when he jumps out of the plane. When the skydiver first jumps out the plane, there is a weight causing an acceleration downwards. Now, when he gains velocity, air resistance will increase. The faster you travel, the more air resistance there is. But the resultant force is still downwards, so there will still be an acceleration. He is still getting faster. But when he reaches a particular speed, air resistance will be the same as weight. This means there will be no more acceleration, because remember, if there is no resultant force, there's no acceleration. No more acceleration means he will travel at a constant speed. He has reached what physicists call terminal velocity, and you do need to know that for the exam. So what have we learned? All objects accelerate at the same pace. They accelerate at 9.8 meters per second squared. Objects have terminal velocity, when air resistance is the same as weight, causing no further acceleration. We're going to have a look at another video now. Hello there. We're looking at skydivers and the forces that they experience. Air resistance is a force which acts in the opposite direction to the direction of travel. It is proportional to the velocity of an object. If an object is moving quicker, it will have more air resistance. Air resistance stems from friction with air particles. As you travel through the air, you hit and pass many air particles. This force, like all forces, causes an acceleration because of Newton's second law. When a skydiver jumps from a plane, there is a large resultant force in the downwards direction. This is weight. As soon as the skydiver jumps, there is no upwards force, but a large downwards force. This resultant force causes the skydiver to accelerate downwards. Now that the skydiver has accelerated, he has gained some velocity. We know that air resistance is proportional to velocity. This means the skydiver gets some air resistance acting on him. As this acts in the opposite direction, there is now a smaller resultant force in the downwards direction. So the skydiver will still accelerate, but to a lesser extent. It will get to a point where the velocity is high enough for a larger air resistive force. When the air resistance is equal to the weight, there will be zero resultant force. At this point, the skydiver will no longer be accelerating. They have reached what scientists call terminal velocity. Where the skydiver is getting near the ground, they will pull a parachute. The parachute will expand the surface area. A larger surface area means the system is colliding with more air particles, increasing air resistance. When air resistance is greater than weight, we will get a deceleration as the resultant force will be upwards. So, to recap, when the skydiver jumps from the plane, they will experience a resultant force downwards. As their velocity increases, their air resistance will increase as they're proportional. This means there is more of an upwards force and less of a resultant force in the downwards direction. There will be a point where the velocity is so high that air resistance will balance weight. When this happens, scientists say you have reached terminal velocity. As they approach the ground, the parachute is pulled, increasing air resistance, putting the resultant force in the upwards direction, causing a deceleration. When the person hits the ground, they will be at a new terminal velocity because of the parachute, so they land safely. So that explains the resultant forces and accelerations on someone who is skydiving. You can interpret terminal velocity and acceleration due to gravity on a velocity time graph. At the start, the object accelerates due to gravity. As the object accelerates, there is more air resistance. This means there is more force acting upwards and the resultant force is lower. This causes the acceleration to decrease. Eventually, where the resultant force is zero because the weight is equal to the air resistance, there is no acceleration. There is a constant speed. It is the terminal velocity. Complete task 16 in your forces workbook if you're following along with your revision workbook, and pause the video. Next, we're going to have a little look at stopping time. When an emergency occurs or a traffic light turns to red, you need to slow down to a stop. The time taken to stop in these scenarios is named stopping time. Your stopping time is made up of two things: your thinking time and your braking time. But during these times, you are still actually moving. So, because time passes and you're moving at a speed, you will go a certain distance during the time that you are stopping. This distance is known as stopping distance. Stopping distance is made up of thinking distance, the distance you move when you're reacting and about to apply the brakes, and the braking distance, the distance moved when you're actually slowing down to a stop. The highway code explains how the speed that you're travelling changes your stopping distance. The higher the speed, the larger the stopping distance. This means the faster you go, the larger the distances for reacting and thinking, and there is a longer braking distance too. We're going to have a look at a little video now. Hello there. We're looking at stopping distance. Stopping distance is the distance a car travels before coming to a stop. It depends on two factors: thinking distance and braking distance. Stopping distance is the thinking distance added to the braking distance. Thinking distance is the distance a car travels in the time that the driver reacts to a change in the road. For example, if a car was travelling along and a traffic light turned to red, the car would continue to travel without applying the brakes in the time that the driver was reacting to the light turning red. The distance that the car travels is the thinking distance. The distance travelled in the thinking time, the thinking distance, can be calculated using the simple speed formula which has been rearranged. Thinking distance is speed times time. There are factors which make the reaction time and therefore the thinking distance greater. Tiredness, being intoxicated with alcohol or drugs, and using a mobile phone can make the thinking distance longer. A longer thinking distance means a longer stopping distance, meaning generally you are more likely to cause an accident. Travelling at larger speeds also means a larger thinking distance, as you go further in the same amount of time for you to react. Braking distance is the distance travelled when you are braking. For example, at a red light, the car will have to brake, and coming to a stop takes time. During this time, the car will travel a distance. There are factors which make the braking distance greater. Driving a heavier vehicle, having worn brakes, or slippy conditions on the road like ice and water all increase your braking distance. A larger braking distance means you are more likely to not be able to stop in time, and you are more likely to cause an accident. Travelling at larger speeds also means larger braking distances. This is because it takes more time to decelerate to the point where your car is stationary from higher speeds. In this time, you will travel further. The total stopping distance is the thinking distance and the braking distance added together. The stopping distance is the thinking distance plus the braking distance. You can work out the total stopping distance by finding the area underneath a velocity time graph. Here is a copy of a page from the highway code. Even for a small increase in vehicle speed, you get a very large addition in stopping distance. So that shows how stopping distance is made up of braking distance and thinking distance. And it also shows that it is very important that you travel at speeds which are suitable for the environment around you, because even a very small increase in your speed can increase the stopping distance by quite a large amount. So let's look at the stopping distance on a graph. At time 0 seconds, there is a light turning to red in front of the driver. This means the driver needs to stop. So here, where time is equal to 0, the lights turn to red, but the driver is travelling at a certain velocity. After a short while of reacting and thinking, the driver decides to apply the brakes here. So after a certain amount of time, the driver applies the brakes, but during that time, he's still travelling at the same velocity. Now the car is slowing down until it's at rest. Here is where this blue line is. This represents the reaction time. So when the driver's continuing at the same speed, he hasn't actually started applying the brakes yet. He's still thinking about the traffic light turning red, or still reacting to it. And then as soon as he starts applying the brakes, there is a deceleration until eventually the car comes to a stop. But during this time, the car's still moving, and this time is called the braking time. But because the car's still moving during the reaction time and braking time, the car will come to a stop after a distance, the stopping distance. You can work out this stopping distance by finding the area underneath the graph. This area underneath the velocity time graph represents distance travelled. What would happen if the vehicle was larger or travelling at a higher speed? Vehicles which are more massive or heavier take longer to brake. Vehicles which are travelling at higher velocities also take longer to brake. So let's look at stopping distances on a graph again. For larger vehicles, their braking time is increased, meaning their overall braking time will also increase. So what factors affect the thinking distance? A driver's reaction time can be increased by the following: being tired, driving whilst under the influence of alcohol, driving whilst under the influence of drugs, or driving without a clear windscreen. All of these increase reaction time and therefore increase the thinking time and thinking distance. So drink driving can lead to an increased risk of collisions, as you simply can't slow down fast enough. What factors affect the braking distance? Well, braking distance is the other part of stopping distance. Things which can affect braking distance are as follows: wet conditions, icy conditions, worn out brakes, or worn out tyres with low tread. So what can affect the stopping distances of vehicles in an emergency? Can you remember anything? Stopping distance is thinking distance plus braking distance. Thinking distance can be increased with drink driving, taking drugs, being tired, or not being able to see the road properly. Braking distance can be increased with worn brakes, worn tyres, icy or wet road conditions. Braking distance is also increased with heavier vehicles, or vehicles travelling at higher speeds. This is because they have more kinetic energy, which needs to be converted into other types of energy to bring the vehicle to a stop. Is it safer to have a lower or higher thinking time? Why? Is it safer to have a lower or higher braking distance? Why? Well, hopefully those answers should be obvious. It's much safer to have a lower thinking time, and that's because you will travel less distance whilst reacting to the change in the road conditions ahead of you. And for the second question, obviously it's safer to have a lower braking distance, and that's because If someone runs out into the road in front of you, if you can come to a stop in a shorter amount of time, you will stop much further away from the accident in the road, and you won't be risking hitting whatever's ran out into the road. Vehicles with too high a stopping distance can be hazardous. If an emergency happens on the road, like a young child steps out in front of you, you need to be able to stop before contact is made with a child. As your speed increases, the rate at which stopping distance increases also gets higher. This means for a small increase in speed, when you're already travelling fast, there will be a large increase in stopping distance. Reaction time can vary from person to person. The average reaction time is 0.2 to 0.9 seconds. The longer it takes for you to react, the longer it takes for you to think about applying the brakes. This means you'll travel further before you put on the brakes, increasing your thinking distance. Reaction time can be measured with the simple ruler drop experiment. One person holds a ruler and the other is ready to catch the ruler when it's dropped. The person holding the ruler drops it without any notice, and then the other needs to catch it. The number shown on the ruler demonstrates how quickly they've reacted. To keep it fair, the ruler should be dropped at the same distance above the hand for each person taking the test. This shows the ruler dropping experiment, where one person drops the ruler and the other grabs it as quickly as they can, and that obviously measures your reaction time. And however far the ruler's travelled through your hand, well, that determines your reaction time. A much more accurate way of measuring reaction time is to use a computer program where a person has to press a button as soon as they hear a noise. This gets an accurate reading as the computer times how long it takes for the person to press the button after the noise is sounded. So this shows someone taking a reaction time test. If you're following along in your revision workbook, complete task 17. Thank you very much for watching. Workbooks and test papers which integrate with these videos and online courses are available at our website, backrowtutoring.com.